Oh, you got it!
Okay, let's talk about some wind corrections. This is not going to be as straightforward as some of our other topics have been. Calculating bullet drop and adjusting for things like barometric pressure, humidity, and temperature are relatively straightforward compared to wind. And the reason for that is, obviously, wind can vary greatly from second to second, and it can constantly change directions, and it's extremely hard sometimes to get good wind readings. And determining wind speed and direction does take a lot of practice, and it's there's only a certain amount of instrumentation that can actually help you out on this. So a lot of this is going to be based on your experience with reading the wind. This is definitely the hardest part about long-range shooting, in my opinion. I would say most of the misses you might experience at long range, if you're really going through this scientifically and you're accounting for everything possible, is going to be your wind. That's what's going to throw you off. Things like barometric pressure corrections, temperature corrections, all that other stuff, angle of fire, is relatively straightforward, like I said before. And you can make those calculations, index them onto your optic, and they're pretty much not going to change that fast. Now, wind, on the other hand, you can have everything perfectly corrected for, and even if you got a really good spotter who's really keeping an eye on the wind patterns, it is possible that at long range, where some of these flight times on these bullets might be a couple seconds, it's possible that when you send the round down range, that you could have a pause in wind speed, a change in wind direction, or change in wind velocity after you pull the trigger. That would severely throw off your point of impact. So that's what makes wind very, very hard to correct for, is because you never really know for sure exactly what it's going to do down there. And there's all different kinds of disturbances and turbulences that might come out of even a steady wind pattern that you might think you have a good handle on. So wind is constantly changing, and there's almost infinite variables that affect wind patterns. And that stuff is very, very hard to account for. So in this video, I'm going to attempt to give you a rundown of some of the real standard methods that have been used to make corrections for wind, and I'm going to try to discuss some of the limitations to those methods. And we're talking about extreme range precision shooting in this video series, so we're going to be shooting farther than most of these systems were developed for. So we're going to have to keep that in mind, and we're going to make modifications to some of these. We're going to take what we can use, and then we're going to add on to it and adjust it as needed. So what kind of effect does wind have on a bullet in flight? Well, basically, in a nutshell, blowing wind is going to push the bullet in whatever direction the wind is blowing. Now, obviously, if you consider the profile of a bullet, you'll be able to make a common sense determination of which direction is going to have the most effect on that bullet. Obviously, if you have wind blowing on the side, laterally, you're going to have a bigger area on the side of a bullet to basically act as a force upon it. So that's going to affect it a little more than if you have it coming straight on. If you're shooting into a headwind, your bullet's pointing on the front, right? So it's going to be able to poke through the wind easier than the side would. Likewise, if you have a tailwind, that's not really pushing from the back. What's going on there is you have a mass of air that's traveling along with the projectile, so that basically the air resistance on the projectile is reduced by the velocity of the wind, however much that would be. So that comes into the drag equation. So obviously, if you have a wind blowing from the left and pushing to the right, it's going to push your point of impact to the right. If you have a wind coming from the front, a headwind, you're shooting into a wind, that's going to produce more drag on your bullet, and it's going to slow it down faster. Therefore, your point of impact will be lower because your bullet's slowed down faster. And obviously, if you have a tailwind, there's going to be less drag on the front of the bullet because the mass of air is moving along with the projectile, with the tailwind. So your point of impact will be slightly higher. Now, the proportion of how much effect these different angles have on this bullet is kind of a matter of debate depending on which system you're using. So we're going to go over a couple of the different systems here. Now, the way most battlefield military snipers learn to correct for wind is by using what's called the clock method, and you can find this in the 23-10 or in the FM 1-3 Scout Sniping Manual. So what is the clock method? Now, for those of you with digital watches, you might not know what I'm talking about, but we have a clock here, okay? And it goes from 1, 2, 3, all the way up to 12 on top, just like a clock. Okay, so this is kind of a way of determining wind direction, okay? And the way we set this clock up is your direction of fire, the way you're pointing your rifle, that we're going to designate that 12 o'clock. Straight behind you would be 6 o'clock, to your right would be 3 o'clock, and to your left would be 9 o'clock. So if you have a wind coming from 10 o'clock, that means that the wind is coming at you from 10 o'clock, from your left and a little bit forward, and it's going to be blowing towards the 4 o'clock. So that's what a 10 o'clock wind would be. If you have a 6 o'clock wind, that means that the wind is coming from straight behind you, and it's going over your head and in front of you. So you always report the wind direction by the direction it's coming from. So you say 2 o'clock, that means the wind is coming from your 2 o'clock. Not going towards your 2 o'clock, but coming from. And the way they have this set up is you have your ballistic data on a card or a table or in a formula ahead of time on a different piece of paper or whatever, and that'll tell you a certain wind correction for a fixed value, let's say a 10-mile-an-hour wind, okay? Now, depending on which angle that 10-mile-an-hour wind is blowing will kind of determine how much of that 10 miles an hour you need to hold off for. If it's a direct crosswind, you can correct for the entire amount of that 10-mile-per-hour crosswind. If the wind is coming straight at you, or coming directly from your tail, then obviously you're not going to correct laterally. You're not going to correct left or right because it's not blowing left or right. So angle is important, right? So the clock method, let's look first at the zones designated, your 12 o'clock zone and your 6 o'clock zone. 12 o'clock is in front of you, 6 o'clock is behind you. Now, they have this divvied up into zones, and this is meant for battlefield snipers. These guys are usually equipped with the M24, the M40. So this is a .308 caliber rifle or a 7.62 millimeter, and they're using usually the M118 bullets, a 173 grain bullet. So your maximum effective range with this cartridge is not going to be much more than 1,000 meters. So we're not talking extreme range here. So that's what this system is designed for. So let's look at how this would work. If you have a wind coming from either your 12 or your 6 o'clock, that is what they would call a no-value zone, meaning that you can look at your wind correction for a 10-mile-an-hour wind or whatever wind you have, and within that zone, you're not going to place any lateral correction on your optic, according to the clock method here. And as you'll see later, we will, for a 12 or a 6 o'clock wind, there will be differences in elevation change, okay? If you're shooting into the wind, you're going to have to come up a little more because it's going to push your point of impact down. And if your wind is coming from the 6, you're going to have to come down a little bit because you're going to have less drag. But we'll talk about that a little bit later. But according to the field manuals, that's the no-value zone. So there's no lateral correction for the wind if you have it coming from the 12 o'clock or the 6 o'clock. The next zone we can look at here on the clock is your 9 o'clock and your 3 o'clock. And that would be like a crosswind, a perfect 90-degree crosswind, or somewhere within that zone. It's kind of generalized here. That's what they call the full value zone, okay? Which means that you would look at your charts, and whatever your chart, if you have a 10-mile-an-hour crosswind, you would account for all 10 miles an hour of that wind with the full value. That's what the full value means. So you would apply the full correction for the 10-mile-an-hour wind on your optic, or you would hold off by that much to correct for your wind value. Now, if we look at the third zone here, there's 4 of them, and this is between your 9 o'clock and your 12 o'clock and your 12 and your 3 and your 3 and your 6. Okay, and this is your this is a little bit bigger of a zone, but anything in between your no value zones and your full value zones are your half value zones. And then this is where it starts to seem a little weird, and it is a little weird. So your intuitions might have been correct if this seems like it's not very precise to you. This does work for, like I said, battlefield snipers shooting inside 800 meters or 1,000 meters. If you're trying to have a quick system that's very field expedient and easy to use, this actually works pretty well. And basically what you do is if you have a wind, let's say, coming from your 10 o'clock, they would consider that to be in the half value zone. So you got a wind coming from your 10 o'clock, you're only going to account for half of the hold-off value. So you look on your ballistic tables for your wind hold-off for a 10-mile-an-hour wind, and basically you're only going to correct for half of that value, whatever that value would be. So effectively, you're only adjusting for 5 miles an hour of that 10 miles per hour. And as we'll see in a minute, there is a better system of doing this, but you should be familiar with how the clock system works, because that's probably what most long-range shooters actually have learned to use. And this does work fine for medium and normal long-range shooting, but for extreme-range shooting, this is not going to cut it. So that's the clock system. Basically, consider the direction of your wind, plot it out on this clock here to see if you're going to apply the full correction value, the half value, or no value at all. And then you simply index the firing solution on your scope for your windage, and you should be pretty close according to this system. Okay, so that's kind of the most common way to designate different wind directions. So how do they figure out your wind speed? Now, we talked about it in a peripheral equipment selection, many different tools for measuring atmospheric conditions. One of those tools was an anemometer. And that can be quite handy for determining wind speed at the final firing position. However, as we discussed a couple minutes ago, when you're shooting long range, it's very possible that the wind, and very likely, that the wind is going to be quite different downrange than it is at your position. Because a lot of times you're going to be taking cover underneath bushes or trees and stuff like that, and that's going to obviously calm the wind down at your position. So you're going to have to determine wind speed by other observations so that you can get a good feel of what the wind speed is like downrange, so that you can more accurately account for all the deflection on your bullet. So one of the common methods for determining wind speed, besides an anemometer, that's a good one for the firing position, but another one is the flag method. And this is only really useful if you have a flag, like a windsock or something, or maybe if you're in an urban environment, there'll be a flag flying someplace. This is a lot of shooting ranges do have flags, so if you're doing like a long-range shooting on a range, you will have the convenience, most likely, of a wind flag hanging out there. And you can use the flag to determine wind speed. Now, this might not work in all field conditions, obviously. You might be out in the mountains tracking elk, and there's not going to be a lot of range flags sitting up there, right? But here's how the flag method does work. You basically consider the angle of the flag that it's blowing, okay? If it's straight across, that would be 90 degrees. If it's like a 45-degree angle downwards, that would be 45 degrees, right? So the angle of the flag divided by the number 4, okay? That equals your wind speed in miles per hour, generally speaking. It's not an exact method, but it does give you an idea of your wind speed. And this is also in the 23-10 manual. This is one of the ways that they recommend judging wind speed. So quite simple. If you have a 60-degree flag angle, you take that number divided by 4. That gives your wind speed. So like 60 divided by 4 would be like 15-mile-an-hour wind or something like that. So that's the flag method. That's also the other method that you might see, like on the Hollywood movies, where the guy picks up the grass and he sprinkles it down on the ground and it kind of blows. What he's doing there is he's getting a feel for the wind direction, that'll show him the direction at his firing position. Now, obviously, he's sprinkling grass at his firing position. He's not looking downrange. But he can consider the direction that blew. You can look at the angle that dropped to the ground at, and that'll be similar to the flag method. So if you're dropping some some light grass or some leaves or something, it'll kind of blow, and you can get sort of the same calculation that you do with the flag method. Well, the flag method's probably a little better than the grass and the dirt because that can vary so much. Some of it's very light, and dust is very light. It might not have the gravity or the mass needed to actually drop. But that's kind of generally one of the common methods you might see. Just thought I'd explain that for you. I would not recommend using the grass or the dirt drop method or even the flag method for a primary means of determining wind speed. Now, those are fine for determining wind direction, but wind speed, that's not going to work as good. The feel method can be used for determining the speed of the wind, and you can sort of tell the direction sometimes, but that can be difficult. And the feel method, and this is straight out of the 23-10 as well, and this actually does work pretty good, is a 3-mile-an-hour wind is going to be real light. You're hardly even going to be able to feel a wind that's 3 miles per hour. Now, as we'll see in a minute, one of our examples, a 3-mile-an-hour wind will throw you off significantly if you do not adjust for it at 1,000 meters. So that kind of illustrates that even though the wind might seem like there's nothing there, you can't even really physically feel it on your skin by holding out your hand. But it is enough to completely throw your projectile off at long range. So let's consider a 3 to 5 mile an hour wind. 3 to 5 miles an hour, you're going to just start to feel it. If you got little whiskers on your cheek or something, on your face, you got your beard, you might feel it on your face just barely. That's a 3 to 5 mile an hour wind, and that is a significant wind for long-range shooting. That you're definitely going to have to correct for that. You're going to miss by a lot again. 5 to 8 mile an hour wind, you'll notice by looking at trees, if the leaves are in constant motion, they're constantly kind of wiggling on the tree, that's probably about 5 to 8 miles an hour. Once you got small trees starting to sway at the tops of them, not the whole tree rocking back and forth, but once the tops of the trees, the long branches up there start swaying a little bit, that's somewhere from an 8 to 15 mile an hour wind. Anything more than 15 miles an hour, and this takes experience, and it depends totally on what kind of vegetation you got, but there's different patterns in the grass or in the bushes or in the trees, depending on what kind of bushes and trees you got. They'll act differently in those kinds of winds. So that's something that just has to be a lot of experience there, how to read the wind. But that's the feel method, and that's other observations as well that you can just use by looking through binoculars. You can look at the local vegetation and see how it's being affected. The best way to actually calculate the direction and the speed of the wind for long-range shooting, and the method that we're actually going to primarily use in extreme range shooting is Mirage. Now, Mirage is a effect that happens when you're looking through an optic at long range. You'll start to see those squiggly, wavy lines. That's what we're talking about, Mirage. And what you have is basically a distortion of the light in the air. As different wavelengths of light go through different density of air, that will change it just like a lens changes light. When light enters different mediums of different density, it changes direction. And the air is hardly ever perfectly uniform. So especially at the surface, because you're going to have different temperature for the ground as it is in the atmosphere immediately above it. So you're going to have heat causing a visible distortion in the air. And that's what Mirage is. Now, obviously, you're going to have more Mirage on certain days. Some days the Mirage might be poor and it might be very difficult to locate. Some days it's going to be very easy to find. That depends on the difference in the temperature of the ground and the atmosphere sometimes, and other things as well. But the primary way to really focus in on Mirage, and the way that most long-range shooters have done this, is you simply take your spotting scope, or if you're the primary shooter and you don't have a spotter, you're going to have to use your rifle scope, or I would still recommend having a spotting scope And this is one area where high magnification is a little bit better, is for spotting Mirage. Now, like we said in our optics videos, high magnification isn't going to help you that much when you're actually shooting. You actually want to turn back your magnification a bit so you can watch your own bullet trace if you're actually shooting a rifle. But for spotting the Mirage, you're probably going to want 16 to 20 power, and that's why I recommended a spotting scope is definitely a piece of equipment you're going to need. That's going to be what your spotter is using. And your spotter is going to be set up almost on your 6 o'clock, just maybe at your 5 or 6 o'clock position immediately behind you and just a tad bit to the right. And they're going to be looking kind of over your shoulder. And your spotters, what they're going to do is they're going to focus in on the Mirage by, you'll look at an object about halfway downrange or about 60% downrange. Not all the way to the target, but something like, at 60% of the range. You're going to focus in on that perfectly with your focus on your spotting scope. Then what you're going to do is you're going to pan up to the target and don't refocus on the target. So what you're doing is you're looking at the target through a scope that's adjusted to be focused in on 60% of the range. So what's going to happen is you're going to be focused in on the air in front of the target at the distance that you focused it, okay? And that's how you get a good Mirage reading. So you can do it a different way. On the old M49 spotting scope, that's just a straight 20 power spotting scope the Army uses. What they do is they basically just focus in on the target and then just turn back the focus about a quarter turn. And that should give you a good reading of the Mirage. But either way you do, it's fine. But you want to basically be focused in on the air in front of the target. So your target will be slightly out of focus when you're reading Mirage. And also when you're shooting, we'll talk about this more in spotting the shot, you're going to leave it slightly out of focus as well so that you can focus in on the bullet trace as it's going towards the target. So that's the primary way of doing it, and that'll give you a good feel of wind direction and wind speed. So if you look at the FM23-10, they'll have a graphic there showing the different wave patterns that you might see with different Mirages. Now, this takes experience, and this picture is kind of hard to draw Mirage. So when you're looking at the 23-10 illustration, that's a pretty good illustration of sort of the idea. It does take a little bit of a trained eye. It's not going to be that obvious usually, but it's just going to be very faint distortions most of the time in the air. But depending on the angle, that'll kind of give you a good estimation of the overall wind patterns within that area that you're focused in on. Now, the idea is that you're looking at the entire column of air from your position to the target, and that would average out into the overall Mirage you would see. And so by doing that, most shooters basically use that as their primary means of wind speed direction and velocity, is by reading the Mirage. The problem is, and this is one of the shortcomings of this method, it's not quite that simple because we focused in on one particular area of the Mirage. In this case we just described, we focused in mid-range someplace, right? So that's giving you a good Mirage reading mid-range. At the surface, and as you'll see after a little bit here, that you're going to need more information than just that, because the wind speed is going to be different there than it is at your position, at the position of the target, at the max ordinate of the bullet. So I'll show you after a little while here how to make better determination of the wind using Mirage. Now, Mirage will be our primary means of determining both wind speed and wind direction, but we're gonna have to get more readings than just the mid-range reading, okay? One thing that we should notice here is if you look at this figure in the 23-10, and I can try to show you some video footage, but it's extremely hard to get the camera to focus in on Mirage. It kind of automatically usually wants to adjust on the solid object behind that, so it's a little difficult sometimes to get a good video footage of Mirage. Plus, it is very subtle, and it would take a really good resolution camera. And YouTube, unfortunately, doesn't usually, it's not well equipped for the real high resolution stuff, at least the way my camera's set up and my downloading software or whatever the heck it is that I'm using here. So it's hard to get good footage of Mirage sometimes. So these illustrations will have to work for now. But boiling Mirage is kind of a mirage that doesn't have like an even pattern to it. If you notice these other mirages, they're kind of wavy lines that are kind of going in a certain direction, and you kind of measure the angle sort of that the lines are going. A boiling mirage is just going to be a big jumbled up mess of mirage. And this can mean two things. Either a boiling mirage is indicating that the wind is blowing straight at you or away from you, which is a good thing, because then your lateral corrections are basically minimized. That you don't have to worry about left and right corrections as far as wind goes if you've got a boiling mirage. But the problem is that a boiling mirage can also mean that your wind is constantly changing directions from left to right. So it depends, and that's another thing it takes a trained eye to get used to. But a lot of shooters don't even take a shot if they have boiling mirage. It's too risky, because that means that your wind is blowing real hard either away from you or towards you, and it could easily make a shift a little bit to the right or left, which would completely throw you off. A crosswind would actually be a little easier to correct for in that case. So some shooters don't even take a shot in boiling mirage. In our 1 mile shoot that we did on this video here, this is a good example of, this was sort of a boiling mirage. The wind was kind of blowing away from us. And so a lot of shooters would think that's a bad idea, but in this case, the wind was so strong, and it was a relatively consistent wind, that after we got all set up, we did decide to go ahead and take the shots, and it worked out fine. But sometimes boiling mirage can really hose you too, so you want to be careful with boiling mirage. Okay, so how do most shooters actually correct for a wind once they determine its speed and direction? And we did introduce you just a second ago to the clock method, where we have our full value, our half value, and our no value system, according to the clock method. So how does this set up anyways? Well, there's two main possibilities. You're either going to have a very detailed ballistics table set up made for wind corrections, okay? And that's going to give you like a wind speed value, 13 mile an hour wind at this range, correct by this much. That's one method of doing it. The other way of doing this is by using a simple formula using a fixed wind constant. Now, a constant is basically just a fixed value. Like in algebra, a constant is a number on its own, or sometimes it's a letter, such as like A, B, or C, or whatever, but it stands for just a fixed number. So that's what I mean by constant. And your wind constant is going to vary for a distance, and it's going to be really only suitable for one basic recipe, like a 600-meter wind correction constant for an M118 ball ammo shot out of a M24 rifle or whatever. So these constants, you're not going to just be able to universally use these for any load you have or any different cartridge or different rifles, but it's something that you would figure out for your weapon system, and once you do have the constants, you can use those to determine your exact hold-off in minutes. So let's just jump into this real quick, and you'll see how it works. So, for example, here's the formula for that the 23-10 uses, and this is how the AMTU teaches wind corrections. This is for minutes of angle. So you would be indexing this correction on your scope, on the windage knob, okay? And basically, you take your range in hundreds of meters. So if you're at 600 meters, you would that would be 6. That would be your range in hundreds. Or if you're at 1,000 meters, you would take 10. So your range in hundreds of meters multiplied by your wind velocity in miles per hour that you've determined using your Mirage method or whatever you're using, okay? And then you take that number and you divide that by your constant for that range. So let's say that you're shooting at 900 meters, okay? And you have an 8 mile an hour wind. How many minutes of angle are we going to apply to our optic here, okay? Well, let's take a look at our different constants. You'll see that it varies with range. And from 100 to 500 meters, it's 15, and then it works its way all down to 11. And the reason for that is because, like we discussed in our trajectory video, just looking at the profile of a bullet, it changes velocity, and the drag characteristics change with velocity as well. and the shape is not linear. It's not a laser beam that we're shooting, so it's constantly changing. So that's why the constant is changing as well. So the formula varies just a little bit depending on the actual range. So let's say we have a target 900 meters away. So our range in hundreds of meters for 900 meters would be 9, right? So we take 9 times, and we have an 8 mile an hour wind, so 9 times 8, okay, for 8 miles an hour. We take that number. Now you got to remember your order of operations. You don't want to just work this all through without pausing. You want to do the 9 times 8 equals a certain number, and then divide that number by 12. It's an order of operations deal. You don't want to screw that up. And if you get a crazy number, that's what you're doing wrong. You got to do the 9 times 8, that's 72. You want to get to the 72 before you start dividing, okay? So 9 times 8, and then you divide it by your constant, which in this case for 900 meters was a range. Our constant for 900 was 12. And that'll give you your minutes of angle correction that you would apply to your optic. So that's probably the most common way that military snipers at least use for long-range wind corrections, particularly in the M118 round. And that's actually a pretty good way of doing it for that round, and it is pretty effective way of calculating it. Now, if you wanted to come up with a constant for a different cartridge, you're going to have to do some math, and you're going to have to really understand how that works. And I can show you how to do that later, possibly when we're doing our ballistics tables. I think there's a better way than doing constants. I did use constants for a long time because that's how I was trained how to do this at first. But there's an easier way to do this, actually. And we'll show you that when we get into constructing our ballistics tables. So that's one of the ways that people actually use to apply hold-off. The other way, like we just briefly mentioned, was by using wind tables. And I think that that's actually more effective because you're either going to have these constants memorized in the field and the formula memorized, which usually isn't a big deal. But you're still going to have this written down anyways. You're going to have other ballistics charts. You're going to have your primary and secondary functions charts. You're going to have a lot of paperwork anyways. You might as well have a really detailed wind table set up, giving you exact wind hold-offs for all your different conditions. And probably the main shortcoming for this system using these constants is, again, like I said before, just like standard conditions are pretty rare. I mean, that's just a point of reference, really. There's no real such thing as a constant when you're talking about the wind blowing around and the atmosphere. It's always changing, and your atmospheric density changes with temperature and barometric pressure. So a 10-mile-an-hour wind is going to have a totally different effect on a bullet depending on temperature. If it's really warm out, the air is thinner, the atmospheric density is less. So a 10-mile-an-hour wind, if it's a warm wind, is not going to push on the bullet near as much as a cold wind would. So it will change your point of impact significantly, just temperature. And another thing to consider, too, is that these constants are developed for a particular set of standard conditions. And those standard conditions, they vary. So they're not really truly standard like we talked about earlier. So that's kind of the dilemma. This does work fine for the ranges intended for like the M118 round. You're only very rarely are you going to shoot past 800 meters. And most target engagements in military settings, even nowadays, are within 300 meters. That's probably the typical range for military purposes. If you're long-range hunting and you want to use constants, you're going to run into the same set of problems the military guys are, and that these constants aren't really constants, okay? They're going to totally vary with atmospheric conditions. And at long and extreme range, these differences in atmospheric conditions will come out and bite you. So next, let's take a look and see how much a crosswind really does affect a bullet at long range. We'll also take a look at headwinds. How much is that really going to drop your point of impact? And we'll look at tailwinds. How much is that going to raise your point of impact? And then we'll take a look at some other factors as well. We're going to look at downslope morning breezes, upslope evening breezes. We're going to talk about a better system than the clock method for getting the wind angles, because the clock method, before you go and memorize that and really get used to using it, that's not really going to work for extreme range shooting. We're going to have to use actual cosines of angles to more accurately correct for those things. And then we're going to take a look at all these different crosswinds, headwinds, and tailwinds, and how much effect does air temperature really have on wind hold-off. Most wind tables that most long-range shooters are using are not corrected for temperature and differences in air density. And we'll see by how much that will affect it, differences in temperature. And also, in this next video, we're going to briefly talk about some of the complications that happen, and we're going to consider the shape of the trajectory again and see how surface wind patterns may not be representative of what's going on at the max ordinate of the bullet's trajectory. And we're going to see how to account for some of those things as well, because you have to do your wind observations where the bullet is actually flying, not just in a straight line to your target. So we'll show you how to navigate through all these different complications and get an effective wind correction, because this is extremely difficult in the field to do, and you're going to need all the help you can get because wind is very, very difficult to manage. So stick around for this next video. It should be coming out immediately after this one. I'll post them just back to back, and we'll get a good handle on wind.